useful things. I'm the president and chief cook and bottle washer.
Fine. Thanks. We're exciting to see the webinar to start. I pass you the presentation now.
Okay, great. Welcome everybody. Nice to see some familiar names. We'll be about probably half an hour or so. So it's not going to be a big chunk out of your day. And I'm really just going to cover the use of our CTD in a few different formats. Sometimes we talk about our instruments as if they're Lego, and they're built certainly using modular components that can be assembled in different ways to make a wide variety of different instruments. But we also have the same CTD being able to be used on multiple different platforms, particularly carried by a vehicle of some kind. We also, of course, make sensors of individual kinds like the Opto that was mentioned earlier. And we build the loggers themselves into bigger systems and sometimes take the loggers and supply them as bare electronics instruments for people to put inside specialized vehicles. So the primary CTD that is an autonomous battery-powered instrument is known as the Concerto. It has the ability to store up to 240 million readings internally. It can run as fast as 32 Hertz. We have 3 different pressure ratings depending on the depth in the ocean that you're wanting to go to. Of course, every instrument that we make has USB, and you can optionally get RS-232 or 485 if you need underwater telemetry, but USB, of course, is the way to go. And it's USB-C, so if you've got USB-C on all the latest computers, and it plugs directly into the instruments. The standard instruments, which are 2.5 inches or 64 millimeters in diameter, always have twist activation, which allows you to start and stop them simply by grabbing the end cap and rotating. They'll vibrate in your hand so that you know that they're running. And it means you can give them to somebody who's not necessarily a trained user and very confidently expect that they will deploy them correctly. And they're available with Wi-Fi as well, so that if you would like to download without touching the instrument, maybe it's suspended from a winch, for instance, or you'd like to use a phone or another device, then you can do that as well. All of our instruments use AA batteries, which are ubiquitous, and if you want the longest possible deployments, you can use lithium AAs, which we typically supply them with. But if you're in a pinch, you can, of course, use alkaline. Or if you would prefer to keep stuff out of the landfill, then we recommend rechargeable nickel metal hydride. They have lower capacity, but if you're profiling, for instance, and you can recharge them every night, then that works out great. Our go-to specifications are simple, straightforward, and WOS standard. So it's 3 microsiemens per centimeter, or 0.003 millisiemens per centimeter in conductivity, temperature up to millidegrees, and pressure at 0.05% of full scale. We have not only the 3 pressure ratings of the conductivity cell, but about 6 or 7 smaller ranges for pressure, which allow you to pick that depth accuracy that you really need, because that's the only one that is a percentage of the maximum reading. So inductive cells, many of you are familiar with CTDs and know that they come in 2 varieties. One is using an electrode-based conductivity cell, and the other is using an inductive cell. There are pros and cons to both approaches, and we like to explain those clearly, because there are applications in which inductive cells may not be the most appropriate for you. And our mission really is to ensure that you're successful in your deployment. So we will happily recommend that you find somebody who uses an electrode cell when that's the best option for you. An electrode cell is typically made as a glass straw. It's quite long, 10, 15 centimeters in length, and very small diameter. And that high aspect ratio is the opposite design really to an inductive cell, which is a low aspect ratio. It's very short, only about 4 centimeters in length, and it's about almost a centimeter in diameter internally. And that means that the water passes through the cell very naturally, and there's great flushing. Even on a mooring line, you don't need to move the instrument through the water column. You don't need a pump. And the biggest power consumption of any instrument is when you have some mechanical movement. Avoiding that mechanical movement allows you to really get much better autonomy out of your instruments. In some applications, it's also very important that you not generate any noise, because you're trying to listen for other noises in the water column. And so being acoustically quiet is important. Electrode-based cells, by their name, clearly have, it's not clear that they're platinum, but they are platinum electrodes, because platinum is pretty inert in seawater, in most places actually. The principle of a electrode-based conductivity cell is a direct measurement that is contingent on that seawater platinum interface being unhindered by anything at all. And the problem can occur that if you have very, very small amounts of biological, chemical, or physical fouling, anything that blocks that interface between the platinum and the water, then you will appear to get a deterioration in your conductivity signal. In an inductive cell, because we have nothing metal in the water whatsoever, we are inducing a current into the seawater. Microscopic amounts of fouling don't affect us at all. It is only once the fouling grows, particularly in the case of biological fouling, grows to the level whether it's physically significant. This also means that when it's chemical or physical fouling, in the case of surface oils or surfactants, those don't affect the inductive cell whatsoever. And cleaning of an inductive cell is trivial. There's no special soap. There's no special care needed to avoid damaging the platinum. You can use a bottle brush or a toothbrush in a pinch. There is a disadvantage to the inductive cell, and that is that the current that is induced into that central passage must, just like all currents, must form a loop. And so it comes out at the top of the conductivity cell, loops around, and comes back in the bottom. And that external current field is also part of the measurement. So any material that is close to the conductivity cell will change that measurement. And our rule of thumb, which is quite conservative, and I'll explain why in a minute, but our rule of thumb is to keep things 15 centimeters away from the cell in any direction. That will ensure that the calibration of the instrument isn't changed at all by the fact that you've got either a metallic interference or a non-conductive, an insulating interference, and whether that's a mooring line or a cage or a guard or what have you. Now we calibrate the instruments with their guards on, and so the guard is completely taken into account, and that eliminates the proximity effect. In the case of Argo floats, we calibrate them with antennas mounted, for instance, and that has the same effect of removing that sensitivity. It's important to say, though, that the impact, for instance, and I don't think I have the slide in this presentation, but the impact of having a mooring line 5 or 6 centimeters away is usually less than 1 microsiemens per centimeter. That is to say, it's better than the accuracy of the instrument. So it's only really if you're looking for the best absolute accuracy possible that these concerns about proximity effects even apply. The drift behavior of an inductive cell is quite interesting. The mechanism is not fully understood, but it seems to be constrained, and there is perhaps an initial aging period, and then the drift stops. And so in this graph, for instance, if we look at the right-hand plot, we're looking at drift per year, and we took 4 floats that had our CTD deployed on them. This is published in JTEC, and 360 Seabird 41 equipped floats from the local area, and plotted them. And the magenta line, the pink line, is the salinity drift per year of those RBR floats, some of which have been in the water for 5 years. It's effectively 0, it's unmeasurable. And there are actually a green line, an orange line, and a red line plotted there, but they're all hidden underneath that magenta line. You can see that the distribution of drift for the electrode-based cell is considerably broader and diverse. So there are a couple which are drifting salty, most of them are drifting fresh. Once you get beyond the kind of static accuracy behavior, then of course salinity spiking in profile applications is the biggest issue of concern. And that's generally manifest, as in this case on the right-hand side, when you're walking through a thermohaline staircase, that you see spikes at the interfaces. So if you concentrate on the black trace, here you can see that there's a spike. Remember that this is from a float that's ascending. So it's coming up from, in this case, over, well, it looks like we're down to about 450 meters, but we're coming up from the bottom of the trace, moving vertically at about 10 centimeters per second, sampling at 1 hertz. And so you see the spiking occurring at the interface, but you also see a density inversion that's occurring over what you know from a physical understanding of the ocean is a stable layer. And that layer should be actually perfectly vertical in terms of density. And so there are 2 time constants in the rbr cell that are used to correct the thermal inertia of the cell. The first is about 60 seconds. And this is corrected not by doing an FIR filter or needing to maintain the time history of the temperature history of the cell, but simply by measuring the internal temperature of the cell, the external temperature in the seawater, and using that as a proxy for heat flow. From that measurement, and you can see the correction in tau 60, there is really only one coefficient that's used there. The second is faster, it's about 8 seconds, and this is following Lewick and Piccolo's model from, gosh, 30 years ago now. And so you can see that that is an FIR filter, and it's got 2 parameters. It's got alpha and tau. The equation's actually been written using beta and alpha, but beta is just 1 over tau. And so those 2 coefficients work for all the rbr CTDs that are used on the Argo program, and the yeah, I think that's all. And the flow rate dependence is actually very small. I think I presented that last week to some folks in the Scripps webinar. We've got a graph that shows that the flow rate dependence from about 5 centimeters per second up to almost a meter per second is largely independent. The same issue occurs on our glider CTD, and this is a graph taken from the Legato. In our profiling CTD, however, we align temperature and conductivity so that very little lag is needed whatsoever. In the Legato CTD for the glider, the thermistor sting is about 3.5 centimeters forwards of the center of the conductivity measurement. And so if you don't know the velocity of your vehicle, that's fine. You can lag it by about just under 1 second. If you do have a flow rate or a vehicle velocity, then you can use that very slightly, but it's not very sensitive to that. Here's some sample data that's taken from a Legato mounted on, I think it was a Slocum glider in pretty shallow waters going through the start of the thermocline. And then, yeah, it was a Slocum. And then some corrections done for thermal mass and lag. Most of our instruments can, in vehicles, not only measure CTD, but also be integrated with additional sensors. And so sea surface measurements or atmospheric temperature is often interesting. Dissolved oxygen, where we're able to take a reference measurement in the air, fluorescence, backscatter, PAR, and the usual kind of host of suspects. The oxygen sensor we'll be talking about a little bit next week, so I'll skip over that this time. Suffice to say that the performance is the same as the under a 4831F, except that the power consumption is about 1/5. And so in battery-powered deployments, these kinds of numbers make a big difference. So our CTD is used in the standalone instruments as the rbr concerto, on floats as the rbr-Argo CTD, on gliders as the rbr-legato, and on wirewalkers, it's typically a concerto or a maestro, depending on the number of channels that are used. The Wirewalker, for those of you who don't know, is a wave-powered profiler developed at Scripps and spun off now through a small company called Del Mar Oceanographic, based in San Diego, just outside. RBR is a good pairing for it because we have a very low-powered instrument. And so a profiler that requires no batteries or no power source except for ambient waves to drive its motion is well coupled with an instrument that consumes very low power as well. Our CTD, the Argo CTD, has been integrated onto a number of different floats. There's a couple more now that are on this picture. Teledyne, the Apex float, of course, is dominant in the Argo world still. Both MRV's smaller air-deployed float, the Alamo, and its larger sibling, the S2A or Solo 2, are both supporting RBR. The French manufacturer NKE supports it in the Argo floats. MetOcean, a Canadian company, makes acoustic listening floats. Pablo is one. And then there are a couple of Chinese float manufacturers. NOTC is one, HSOE, PHM 2000 is another that support and integrate the RBR. The deployment of the air-deployed floats is straightforward, and I think Steve Jane's actually on the call today. This is one without Steve. Steve is usually pictured in the video throwing the float off the back of I think it's a C-130. This, I think, is a small, like a Beechcraft or something like that, and it's going out through the chute, parachute opening, and then the parachute is dumped. These are often used in front of hurricane fronts and kind of make a picket fence deployment of 10, 15 floats at a time. Being made of without any glass, without any electrodes, and being a fairly compact instrument means that we're very robust to high shock and vibration loads. Here are a couple of pictures of the CTD mounted on some floats. On the left, we've got the Apex Teledyne float. On the right, this is the Ephemer Arvo float, and that's inside the test tank. Sorry, I say Ephemer because of the label right there. It's the NKE float developed at Ephemer, and that is the Ephemer test tank in Brest, Northwest France. We also have a deep CTD suitable for the Argo program. It's quite diminutive in size. It's about 33 centimeters long. Shown for scale there is the Seabird 61, which is almost double the length. In fact, it looks like we're about the same length as the electrode cell, which is somewhat hard to believe. So that's rated to 6,000 meters. And we actually have two variants, both an inline variant and a transverse mount. That transverse mount is well suited to bidirectional sampling, where it doesn't matter if the flow is from the upper or the lower, depends on whether you're doing the upcast or downcast. Of course, when you're taking the energy to take the hydraulic energy required to move the float down to 6,000 meters is substantial. And so you don't want to waste the trip by not measuring. So you want to have a CTD that's equally well able to measure no matter which direction it's traveling. The Legato CTD actually originated out of a request from Teledyne to build a CTD that would fit in their 7x2 inch bay. We have both a dry bay and a wet bay variant. Nominally, they run at 2 Hertz, although they can run up to 16 Hertz, and they have both a long-term deployment thermistor with a time constant of about 1 second and a fast thermistor available, which has a 100 millisecond time constant. Again, no pump is necessary, and they're a drop-in replacement really for the GP-CTD, which is the reason that people came to us asking for that. The big difference again is that for the same measurement spec, the power consumption is 1/10 of that people were using. And the top of each sensor is, that radius is designed to integrate into the diameter of the float you're on. So there's a Slocum model, there's a model that fits actually in the slightly conical Seaglider rear bay hatch cover. There's a unit for smaller AUVs like the British Aerospace / Riptide. It's about 10 centimeters in diameter. This has been deployed also on the AMT Haiyan glider coming out of China. This flushing, of course, is something that doesn't come by accident. We spent a lot of time optimizing the flow through the cell so that you can see the velocity of water inside the cell, particularly in that lower graph, is the same as the velocity in the free water, that yellow color. And that's by design to ensure that we get water coming through the conductivity cell and not being diverted elsewhere. When you push a straw through the water, water wants to go everywhere except down that central hole. And so you must use a pump with all the consequent problems that causes. This was some early deployments of a fake glider. This is at Woods Hole at the Quissett campus in the Clark Labs double diffusion tank. This is, it was Ray Schmidt who designed and built this tank first time around. In fact, I think most times around. It's about 10 meters tall. It's a fantastic facility because this double diffusion tank allows us to set up a fairly strong interface somewhere in that 10-meter interval. Usually it's in the top 5 meters at the moment. In this graph, you can see the interface is about 3 meters down. And here we're demonstrating the flow rate dependence of the measurement. And so you can see that we took this legato and dropped it on a winch at a controlled 10 centimeters up to 100 centimeters per second. And really, you can see a slight difference at that 10 centimeter per second level, but all the others are pretty much coincident. Now, the double diffusion tank does suffer a little bit that when you drop a torpedo of this size through it, the interface is disturbed. And so repeatable measurements are something that you have to be very patient in order to attain. But you can see the point here that there is no substantial difference according to flow rate. This is the integration on the Slocum. There are actually 2 positions. So one is on the forward science bay on the top, and the other is under the wing for the purposes of this photo. And because the instrument is in a travel case, the wing has been removed, but you can see it in the right-hand photo that the legato is mounted under the wing, just allowing more flexibility in terms of other use of payload area. Here is the mount on the Seaglider, as was University of Washington, as was iRobot, Kongsberg, Hydroid, and now I think it's Huntington Ingalls Industry, HII. And thanks to Luke and Jeff for letting us use these photos of their deployment. This is the French glider, Alcimar, and we're mounted in the bow here alongside, I think it's an oxygen sensor. And sometimes I believe there's a turbulence sensor mounted on the other side. Oh, and we're jumping back to data from UW, from Luke, deploying in Guam. Maybe it's me with the background noise, or it might be a motorbike passing somewhere else in the world. So finally, we're going to chat about the Wirewalker. The Wirewalker, as I mentioned, is this wave-powered profiler, and it's a fascinating vehicle by virtue of its simplicity. if you're going to have moving parts, you want to have as few as possible. And Rob Pinkold, Drew Lucas, Mike Golden, Tyler Hugan have done an amazing result, amazing work in the design of this vehicle. The center of it really is where the only moving parts are, and they're a ratchet. And so as the cable moves up and down due to the buoy motion that's supporting that cable, this ratchet pinches and then releases onto the cable. If you like, you can think of it as a mechanical diode or a rectifier. And so it converts that vertical motion of the buoy in both directions into single direction motion of the profiler, which ratchets its way down through the water column. Yes. When the profiler gets down to the bottom, the ratchet is released and it ascends under buoyancy only. And so it's completely decoupled from sea motion. For that reason, if you had a choice between which way you would mount the sensors, we actually mount them facing upwards so that they are the best data, the cleanest water is measured when we're decoupled from the motion of the vehicle completely. Here's a kind of exploded view, if you like, showing the Wirewalker, and that it's an absolute pack horse in terms of being able to carry instrumentation and can be equipped with all manner of different things. The rbr system not only gathers data, but also telemeters it up the mooring line using our inductive modem. And so we have a modem that can clamp around that jacketed cable, slide along the cable as the instrument's moving, and be able to get 8 Hertz data up the mooring line for about 5 channels in real time. So that gives not only kind of an engineering confidence of that the vehicle is still moving correctly, but at the top then we have telemetry both over Iridium and GSM, depending on which is in range. And this allows you to get the data in real time without actually being close to the instrument. And you can leave it in a drifting mode, not just anchored to the seabed, which is useful in certain situations. But here is Susan Whiffles on the Investigator with myself last November. You can see the buoy is very small, about 70 centimeters in diameter. And we chucked this off and left it to drift for 2 weeks and steamed around. And then after 2 weeks, went back and picked it up. So this unit at the top is the rbr Cervelo, the brains of the unit. And that handles the kind of redundant storage and telemetry from the instrument that's down below. The data that you get from this is absolutely glorious, because profiling at about 50 centimeters per second continuously, you can get thousands and thousands of profiles. And this is, to be able to do that in a hands-off mode is trivial. Of course, being able to get that data back while you're on the ship or from your office is important. And so we have both a website and kind of APIs to be able to pull that directly into whatever code you like for post-processing. So that really wraps it up. The CTD, again, that we make has been deployed in a number of different form factors tailored to particular vehicles. And once you achieve this level of accuracy, then the key differentiator between CTDs that are available to you is the power consumption. And when rbr consumes 10% of the power consumption of the next CTD, then that really permits great autonomy to your deployments. But of course, the other thing that's important is that you can pick up the phone or send an email and get a fast response. And we spend a lot of time inside rbr concentrating on being responsive. And those of you who have worked with us will know that. And it's something that we are, I think, rightly proud of. I'm going to see if there are any questions. Thank you very much for coming along. Didier, are you around?
Yeah, and we don't have a question on the chat session.
Oh, there we go. Yeah. Let me see if I go my stop share anyways. Yeah, so happy to take any questions from anyone who's out there. Just scanning the names, good to see some recognizable names again. Yeah, looks like Steve Jane is possibly on the call as well.
Yeah, I'm on, Greg.
Good to see you. So we're continuously, we're doing these webinars, this series, once a week, but we're always looking for things that you'd like us to talk about. And so if you have any suggestions on material or even the tone and kind of level of the material that you'd like to have discussed, please let us know. You can do so in the chat or send an email through to info@rbr-global.com. Webinars are a pound a penny. There's lots of webinars out there at the moment. And so if there's something that interests you in particular, don't hesitate to let us know and we tailor it to that. Thanks, Glenn.
We have a question from Kevin Martin.
Okay.
Is there any way in-house we could calibrate for the surrounding change?
Yeah, absolutely. So the proximity effect causes a fixed offset in salinity. That is, it's just an offset or a bias in salinity. And so what you really need is a bath of water which you know its salinity. And so if you need to have, if you have a salinometer or even if you were to take the CTD and put it in that well-stirred bath and make a measurement, and then add the mooring line or the guard or the cage and make a second measurement, the correction factor is simply that offset that you read between the two. It's multiplicative in conductivity, so it's easier to do it in salinity terms where it's just a fixed offset. So it's very easy to do that. You can also do it against a reference salinometer if you need, but generally you don't need to do that. You can just take the same instrument and deploy it twice. I hope that answers the question, Kevin. Fiona, do slocums need to be calibrated for a specific payload bay? So we have what we know as the K factor. So the K factor is, it was originally the Kongsberg factor, and it's a scaling number in conductivity or an adder in salinity that's used to accommodate for those different arrangements. And yes, when you are mounting the CTD under the wing, you need to apply a different correction factor, a K factor, than you do if you're going to be mounted on the bow. And that can be done in the Ruskin software. Webb know how to do that themselves as well. But if you attach the instrument to Ruskin, then it will say, oh, this is a slocum rbr legato, and it will ask you which K factor. And the K factor has a label next to it, which says something like bow mount and underwing mount. So you don't need to calibrate them, and they don't need to go anywhere for calibration. They've been characterized here at RBR with a glider body. And so you can also take one off a slocum and mount it in an AMT, and you just need to apply the AMT K factor. Does that make sense, Fiona?
There's no more question, Greg. We can stop this webinar now.
Okay, great. Well, thank you all for coming.